Okay, we'll get going. We have Doug Zentz here today from Ferris State University, where we send many of our students. And Doug has been teaching at Ferris State University for 13 years, very familiar with HVAC, was in and worked in the industry for 23 years. So, and he's coming here to give us a perspective on the energy code, which I need education on, we all need education on. So, so please give him your attention, and thank you for coming, Doug. Appreciate it.
Thank you, Dave. How are we all doing today? Good. Well, I'm going to try to make this as lively as I can because I know I'm standing between you and lunch. So we're going to try to make this as interactive. Just a quick show of hands so I know the kind of crowd, though I'm kind of assuming. How many of you are architectural students? How many of you are engineers? Oh, good. There's a few. How many are environmental? Okay. And then I guess the ones that didn't raise their hands, I'm going to say other. Political? Construction management? Okay. Okay. I want to get across kind of a feel for where you're coming from. How many of you have heard of Standard 189? Good. Good. Well, as we get going here, this slide basically is echoing a couple of things because this is actually a presentation that I give for ASHRAE. For those of you who know who ASHRAE is, I'm what's called a distinguished lecturer with ASHRAE, and this is one of my topics that I travel and speak on. I actually gave this presentation for USGBC here in Grand Rapids a couple of years ago. Just a reminder, cell phones, please keep them off. And I'm going to try to observe ASHRAE's no commercialism policy when we get started here, so I'm not going to name any names of companies or specific products. If you ask a question, I just please respect that as well. I think this battery's dying. And some of this is my views and not necessarily ASHRAE's, so also keep that in mind. Well, as was mentioned by Dave, one of the core areas of this presentation or this standard is dealing with energy. And so if we look at energy in its very basic form as far as consumption of energy, and we look at the human race, now whether you're going to talk about this as North America or you're going to talk about this globally, there are mainly 4 areas in which energy is consumed that we can put most energy consumption into. It's either going to be in some form of residential construction or residential buildings, commercial buildings, transportation, and that just shows highways, but I'm going to include trains, planes, automobiles, everything, all transportation. And then there's industry, manufacturing. Those are the 4 main areas of energy. And if I'm going to take the top 2 and even go more basic and just say buildings, and the fact of the human race in buildings, that's 40%. That is the largest area of energy consumption in the world, is buildings. And that's because buildings consume a lot of energy. If we start talking about utility energy in the form of natural gas and electricity, that's a public utility energy, that is by far the biggest sector of energy consumption in buildings. It's about 70% of all utility energy is going to a building for its consumption, not industry. Industry is a small player in that. So buildings are the low-hanging fruit. Now, one of the things that I want to talk about here is think about the last 30 years. Now, I know some of you may not be 30 years old, but where has the transportation industry gone? Have there been forced by the federal government to be more energy efficient? Yeah. What about industry? You think industry has been forced through various governmental agencies to become more energy efficient? Yeah, and it's not so much that they have to. Their existence depends on it because it's a bottom line cost to their widget, whatever they're making. So they're forced to do it. The one area that's not forced to do it is buildings. Now, you might talk about energy codes, but do the energy codes apply to existing buildings? No, they don't. And if you look at our building stock today and say, what's our building stock going to look like in the year 2030? And you can go to different people and get different numbers, but it's somewhere in the vicinity of 90 to 95% of the building stock that will exist in 2030 exists today. So if we start talking generically about buildings and energy consumption, we're talking about today's buildings, not changing code for new buildings, today's buildings. And that's the big difference. Buildings represent a tremendous amount of either consumption, waste, or potential elements that affect us as the human race. And I'm really, really happy with Matt's presentation before mine because it really kind of sets mine up. If you look at all those elements there, it's just buildings represent an awful lot, especially that CO2 emissions. That's global warming or the environment. It's a third of North America's CO2 carbon footprint, buildings. And that's a huge piece. I'm going to have troubles with this, I can see. If I look at, and there's a lot of different charts out there to illustrate this, but if you just look at some of the major areas like industry, transportation, and buildings and plot energy consumption around the world, there's one trend, with no matter whose data you look at, that comes out screaming at you. And that is the fact that building energy consumption is on this ramp of more, more, more. It's kind of like Tim the Tool Man. I want more. Okay? And why is that? Why is that? Well, think about this. What's going on in China and India today? Has been for the last, say, 15, 20 years, China and India. They want to be like you. They want to be like me. They want the 3-bedroom, 2.5 bath, 2-car garage home. They want the shopping mall. They want all the conveniences in life that we have. So they're building that infrastructure. In fact, you probably don't know this, but about 8, 9 years ago, whenever it was that China held the Olympics, there was a growth spurt in China where they were lighting the match to a brand new coal-burning plant for electrical power at the rate of 1 a week. Think about that. Think about the global aspects of that in both consumption of fuel, byproducts of combustion, and how that's going to impact fuel demand globally for the future. And with that, this is a chart from another source that shows that projecting out, and these numbers at the bottom, the last ones out here are 2030. If you look at the projection of where fuel sources are going to come from, even if we step up our game in renewable energy, we are still going to be heavily dependent as a human race globally on fossil fuels. And the biggest reason for that is the demand for energy is outgrowing the pace of production. Globally, we want more power. We want more energy as a human race. And so, even though we could expand renewable energy and all the science that goes with that, we're still going to be dependent on fossil fuels. Should I be pointing this up when I click it? What'd you do, Matt? What was your secret? You just clicked it. Okay. Okay, I want to go through a little exercise with you. If we look at people around the world and say, how much energy does a person consume, average person in the world? Well, there was a study done that says the average person in the world globally consumes about 200 kilowatt hours of energy on an annual basis. This is not a convenient time for this to die. Okay, in China, it's about 1,800 kilowatt hours. In Europe, it's 6,000. For those of you who saw the quick glance, what do you think it is in North America? 16,000. Okay, we are viewed by other parts of the world. You can snort and oink right now. We are the energy pig. North America is viewed that way. So anytime you hear anything that involves the European Union or United Nations or a global representation of energy consumption, we are considered the evil. Okay? How many of you are familiar with the Kyoto Protocol? Okay, how many understand why the United States did not endorse that? Okay, we did not endorse it for a lot of reasons that would have caused economic chaos for us because of this and the fact that the way the world views us, there were restrictions built into that protocol that would have shut down certain things in this country that were directly related to this energy. I'll give you one example. We would have had to reduce energy consumption in North America, and it would have targeted certain industries specific to carbon footprint. One of those examples is any kiln process that takes limestone and makes cement that you can then mix in to make concrete, that process of taking limestone and producing cement. That industry would have died in North America because of this. Now, what do you think would have done to construction? All you CM students, what do you think it would do to construction if all of a sudden every supplier that wants to make concrete in North America would have to buy their cement mix from the Far East or Europe? Oh yeah. What about the quality of the concrete you're going to get out of it? Questionable and costly. What would that do to our construction industry? It would significantly impact it, wouldn't it? So I applaud our politicians for not endorsing that protocol, but that is a small hidden example of what happens in global arenas of politics when you start talking about energy. It touches too many things and could impact us greatly. Yes?
How are they then able to get through the next?
Oh, I love someone who sets me up. Yeah, I'm going to answer that in some slides coming up, Dave, okay? Hang in there with me. Okay. On a different note but related, how many have ever heard of the IPCC? Okay, International Panel for Climate Change. It's part of the UN. They've identified buildings as the greatest impact to global warming and climate change. It's not transportation, it's buildings. And that has to do with the direct and indirect ability of buildings that touch the carbon indexing of whatever nation or part of the world the buildings are in. Okay, I'll just go, yep, worked great. Well, it did. Might be this button. I'll push harder. Okay, this is the European Union. European Union is ahead of us, by the way. And whenever you go to any of your industry or organizational meetings, whether it's construction management or architectural engineering or wherever you go to, like whenever I go to the ASHRAE annual meetings where it's a global conference, I always go to at least 1 or 2 technical seminars where the Europeans are talking. In fact, I'm going to reference one of them here in a little bit. But, because they're way ahead of us. They're 15 years in front of us, easy, of what's going on in the world. Oops, I pushed it too hard. They started this back in 2003, building energy labeling. Just like if you were going to go out and shop for a brand new car and you have the sticker in the window, what are the great big numbers that are on the sticker? Don't say price. Miles per gallon, efficiency. And in fact, if 2 people are on the street talking and the topic of efficiency comes up from a big picture standpoint, what is probably the most common thing that they would be talking about in the areas of efficiency? Probably transportation efficiency, because that you see that on the news all the time. Okay? Well, when you start talking about building efficiency, and Matt was referring to EUI in his presentation, and EUI is a growing topic, and there's several different terminologies that are all loosely meaning the same thing. But it's really a measurement of getting back to that sticker in the window of like a brand new car. So if I say, hey, my building's consuming 90,000 BTUs per square foot on an annual basis, how many of you would have any idea whether that's a good building, average building, or poor building? You wouldn't, because you wouldn't have any idea. Okay? Well, it's going to be forced on us. And the reason for that is it started in Europe with this building energy labeling. And with that, you see the 2 numbers, 48 and 83. Very quickly, just to digest this as to what it is, the 48 means that's my intended, I feel that it should be that number through the design analysis. Like Matt was talking about his numbers being around 20. Now his numbers were kBTUs per square foot. These are joules per square meter, and I think it's kjoules per square meter. Okay? So, but look at the 83. The 83 means actual, because in Europe they do a 2-step process. One is the intent, the design. That's the 48. That's what I think it's going to be. The 83 means, okay, project's done. We've commissioned the project. Owner's taken over the project. Usage. Gone through at least the full year. Now someone comes in Europe that doesn't exist here in North America called a Certified Energy Assessor. All you engineering students, ears ought to perk up. This is a new career path. Doesn't exist in North America today. That person comes in, analyzes the building operation, and then also goes out and grabs those utility bills from the owner and certifies that the building, yep, that's your actual footprint of energy, and yep, your building's operating as it was intended and designed. Then in Europe, they have to take these 2 numbers, build something that looks like this chart, and the owner has to then put it in a plaque at the front door of the building. How many building owners do you think out there right now would be really proud of having a plaque at their front door that illustrates their building energy consumption? I think you're high. It's a low percentage, and I don't think too many people would want it. They're doing it in Europe. It started in 2003 with governmental buildings. Around 2007, it morphed into the public sector, and now this plaque has morphed to where every company, or every country, I should say, every country in the European Union has their version of it. And by code now, every building that's bigger than 1,000 square meters, or any project or renovation bigger than 1,000 square meters, must go through this process. Now, the United States and the Department of Energy has been looking at this really, really strong. And in fact, this is what we're using here in North America. This is a voluntary process right now. ASHRAE started this, the Building EQ program, several years ago. We actually have a few buildings here in Michigan that complied with this and did this, okay? But it's still voluntary. There's no code compliance. There's no meat to it. It's all, I hate to say this, it's kind of like LEED. There's nobody forcing you to do it. In many cases, there's no teeth in it. It's just another version of a rating system, which I'll talk about in a little bit. But this is kind of what is here now. The Department of Energy has looked at this. They've looked at what's going on in Europe. And in the last two acts of Congress that we're going through trying to become legislature, first one was in 2009. The next one, I think, was 2012, if I remember. Both of them got shot down because right now in Washington, we can't get both sides of the aisle to agree on anything. But as soon as they do agree on something, some form of this is going to hit North America. And that's going to create a whole nother awareness to the built environment on efficiency. Oops. How many of you ever heard called CBEX? Oh, good. CBEX started by the Department of Energy back in 1979. And every time the United States would go through a new energy act, it funded this in two parts. One part was to go out and take another sample size, 5,000 to 7,000 actual buildings in North America, to get a survey done of what their actual energy consumption would be for the building. The other part is whatever the last survey was done 3 or 4 years prior to that, there's more funding that's now available for someone to crunch all the data, create all the tables, and make it public information. Okay? I have a whole nother presentation that touches on this. I'm just going to give you one snapshot, and I know this probably breaks every rule in the book with PowerPoint, but I'm doing it for a reason. The top numbers, where it says all, then 1A through 7, those are the climate zones. For those of you familiar with the climate zones of North America, when it comes to looking at the various different elements that touch code and the building codes to climate location of building. Then on the left-hand side, you've got your various different areas or types of buildings. And this represents from the 2003, so the time I did all that, that was the latest information that was public that you could see on the DOE website. These are KBTUs, so these are EUI numbers. These are KBTUs per square foot of energy. Average for that building type in that climate zone. And without memorizing all, oh, by the way, we're right now in climate zone 4A. Okay? So if you look at that, those are the numbers that would pertain to right here. But what I want you to look at and remember is one number. Upper left-hand corner where it says 90. That means all North America, all building types for commercial buildings. The average. It's like if I said, hey, I drove my pickup truck here. I'm not going to tell you what brand. I brought my pickup truck here, and I hit the computer to see what my average mileage was on my pickup truck. And if I tell you I got 18 miles per gallon, you have a number in your mind real fast, whether it's average truck, good truck, bad truck, right? Well, again, if you want a number in the back of your head, average building, North America, commercial building, average EUI, 90,000. And Matt was talking, the numbers were between 80 and 100, so you're right there. Okay? The one thing that is going on in the background with the federal government, the DOE, is there was in 2007 an Independent Energy Act that created these standards for public government buildings, or federal buildings, I should say. So if you're doing federal work, or you're aspiring to do federal work down the road, the federal government is mandating, saying, okay, per that Bent's baseline of 2003 EUI CBEX data, these are the savings they want to hit. Notice that out at 2030, they expect all of their buildings to be net zero. Pie in the sky, in my opinion, but hey, it's nice to have big aspirations. This is a slide that I can't take credit for. I have to credit where credit's due. ASHRAE had a past president who died suddenly, and I was able to get this information from her. And I'm having a senior moment here is her name. It'll come to me when I'm in another slide. Anyway, this is a study that was done that took that CBEX information, 90,000 BTUs per square foot annual basis, and say, you know what, we're going to model all that data. So they did a modeling exercise. Gave someone some money and said, let's go model all that data. Well, the modeling showed it came up short of that. And I'm going to touch on what Matt was saying when I do this, because this is something that most consulting firms, consultants do. They underestimate one area of a building's energy operation that's almost impossible to know what it's really going to be. Can you think of what that might be? Yes? Yeah, well, okay. You just said one thing. Where does a computer get its energy from? Plug loads. Plug loads are the one element that is normally undervalued. That's one of the takeaways you should get from this presentation. Plug loads in real world represent 20 to 25% of the building energy consumption. And most people think it's much less than that, because they're identifying with bigger pieces of equipment. Okay? Yes. And I've got other material that will show that, and right now, okay, here we go. I double-clicked it. I'm sorry. That data that I just set up there at 79 with the computer study, they reran all the buildings in computers again. And they said, what if we brought all that building stock up to, at the time, the most current energy code out there, which was 90.1, and this was done in 2000, the study was done in 2007, so the most current version at the time on the code books was 2004. And they said, if we bring all the buildings up to current code, it drops the energy consumption a little bit. Still haven't hit near zero, nowhere near Matt's numbers of 20. And then they reran it again and said, how about next technology? Best lights, best walls, best roof, best of everything. Same buildings. Haven't changed the people, haven't changed the utilization of the spaces, just changed buying the best to make the building, which means you're going beyond code. Repeat after me. Code means one thing. The worst building I can legally build. Because that's exactly what it means. So they went to a much better building that they could build. And they dropped from 80 predicted, 79.2, down to 40. They cut their energy consumption of a building in half by having the guts to go better than code. And last they said, okay, what if we add PV to the building? And they were able to get the entire building stock of North America down to 12. Notice it wasn't net zero. That's because there's a lot of buildings that will never get to net zero. And there's good reasons why. Okay, based on all that, and I'm setting up, I haven't even gotten to the standard yet. I'm just giving you the background as why it's there. I hate this. There are because of the evolution of everything I've told you so far over the last 15 years, there were a lot of cities out there that wanted, or parts of our country that wanted, a code language or something to code that they could put people's feet to the fire as to, I want a green building. Okay? LEED came about, but what's the one problem with LEED? It's voluntary. None of it's written in code language. And you can pick and choose what you want. Okay? So what it did was it created various areas of the country, and here's one example out in California, to come up with their own attempt at what is a green building. Okay? And that created, in reality, if you do a lot of research, a lot of legal issues. Because again, it wasn't really written in code language. Because you have to follow certain standards to do that. Okay? And what it did at the bottom is it created an awful lot of opportunities for lawyers. And I'm serious. Now, there are a lot of rating systems out there, and there was a question earlier that someone asked about rating systems. I don't remember who it was, but there's a lot of rating systems out there. And whether you're doing green globes or you're doing LEED or you're doing something else, and there's all sorts of other stuff out there worldwide. They all have one flaw, and that is you don't have to do everything they say because they have different levels of obtainability in their standard or rating. Okay? There's nothing that forces everybody to look at site development and all areas of site development, or all water usage, or all energy, or doing sustainable practices after it's constructed. It's just, there's suggestions in there, but you don't have to do it all. So what that created was, and time going fast now forward, is somebody had to step forward and do this. And I'll be honest with you, the reason ASHRAE did it is because ASHRAE's been doing it for a long time. It goes back actually to the 1970s and the development of Standard 90, ASHRAE Standard 90, that actually started in 1975, shortly after the first oil embargo in the 70s, of trying to address this thing called energy consumption in buildings. It has morphed over time, and many things have happened, and basically, here's what we have today. Standard 189.1, and it's all about, in code language, what is a commercial green building. And it covers these areas: site, water, energy, indoor environmental quality, materials, and construction. It is incorporating within the standard 3 current ASHRAE standards. The top one on 55 deals with human comfort. That is, defining how you and I are determined to be comfortable inside the space of the built environment. So it's looking at our activity levels. What are we doing? Am I standing here? Am I talking? Am I moving about? Am I seated? What am I doing? How am I dressed? That's another element. If there's movement of air in the space, where is it coming from and how fast? And there's also other elements beyond that. But it's also looking at all those elements so that you feel comfortable. And one of the ways that you can do that is to control one thing in the space. And here's where the Europeans are very, very much ahead of us and smart. And I have to applaud Matt in the final choice of his system about going radiant. And here's the reason why. If you can control the mean radiant temperature of all the objects in the space around you, you have a really good chance of being comfortable. Think about this. If you as a person walk into a space, if you've ever walked into a freezer or a low temperature refrigeration room, a cooler, for those of you that might be bartending, you walk into the keg room where they keep them cold. I'm just using it as an example. Anything where you're going to walk in and it's a totally different temperature, you immediately feel the impact on your skin because either you're losing energy to the space or all those objects are pushing energy on you immediately. So controlling the mean radiant temperature of the floor, the furniture, the walls, the ceiling, anything that's an object in the space is a huge step towards solving that standard. Okay? So having radiant elements of heating and cooling in a space, big bonus. Europe's taken to the next step. They actually do drywall with capillary tubes built into it. So the entire wall becomes a radiant panel. They sell modular furniture with capillary tube systems built into the furniture, so the furniture becomes the radiant object. They're not only just the floor or the ceiling, they're doing everything. And so they're really, because they're doing that for one reason, to minimize the air that we have to pump and push around in the building. Because air is a gas. Gases are compressible. It takes a lot more energy to pump air around a building than it does water. So that's why they're doing it. Then there's ASHRAE Standard 62.1, which is on what is indoor environmental quality. They call it air quality, but it's really environmental quality. And then 90.1, which is the basis for building energy code in most states in North America. It's also this. It's built on the platform of LEED, which means it's taking all the areas of LEED and embracing this up here and creating now code language for everything. And that's the big difference. Here's a latest version of that from 2014. It started in 2009. It was updated in 11 and also 14. By the way, if you're going to take a look and go look at this, I would encourage you to look at what's called the user's manual. It actually gives you examples and explains everything. It's about 300 plus pages thick. It's a big standard. Covers a lot of stuff. I am not going to cover everything, especially since I've only got 15 minutes left and I've got about 50 slides left to go through. So we're going to go real quick. Okay, so its intent, it was sponsored by the following organizations. USGBC was a platform sponsor of this standard. The Illumine Engineering Society, and ASHRAE. These three independent societies created this standard. At the very end, there was one more agency that got along for the ride, and that was the International Code Council, because they were creating their version called the International Green Code at the same time. And so they decided to come together, shake hands, and make sure that they were both going on the same path to create virtually the same thing. And there is verbiage in both International Green Code and ASHRAE Standard 189.1. This is basically, if you follow one, you're in compliant with both. Okay? So that's an important thing to understand. The standard applies to basically everything that 90.1 would do, which is basically any building that's a commercial building that's not residential or low rise, and it's not a design guide, it's not a rating system, it is a code language of what is compliant. And even if your local authority is not using this standard, it is a big time message of what is to come in code standards in North America. Okay? So if you're not familiar with this standard, I would say get access to to this. How many of you are Ferris students? Any? Okay. Ferris Flight Database, the library, they have this in one of the databases that you can actually go look at. It's going to take some hunting, but you can find it. The purpose of this is basically to give you a complete package in code language of looking not only at the energy impact or the environmental impact of a building, but everything from site design, construction, and plans of operation. The plans of operation are a huge step. That's one big, big bonus that nothing before it really looked at. And it's creating a balance of all the various elements that go on in that process, along with this, the need of the presence without compromising the future. Going back to what Matt was talking about. So this standard is code language for just about everything he was talking about. Here's the various areas of the standard. Those of you familiar with LEED, if you read down the list, you're going to see, oh, that's LEED. It is the same areas. Plans and operation, big difference. A lot more meat here and a lot more than LEED does. Okay? Basic structure of this, it's written because it's code language. Every area starts with a scope. Then it looks at what do you need to do to be compliant in short description. It is then giving you a list of the mandatory things you must do, thou shall, in every area. It's no longer a Chinese smorgasbord like other rating systems where I can pick one here and one here and one here and feel good. This is now feet to the fire, have to. Then there's two paths you can go down. And then this is in each area. One is the prescriptive path, which is kind of like following the bouncing ball. Do these things and you're compliant. The other path is performance-based. They give you some guidelines and some performance metrics that you must meet. And if you can prove you've done that, then you don't have to do the prescriptive. And I'll give you an example you probably could easily relate to, because it's kind of the same thought process that's in ASHRAE standard 90.1 for the energy code, for those of you that are familiar with that. Let's say, I'm going to pick on the architecture students here for a minute because that's my favorite thing to do. I'm sorry. Let's say that the architects want a nice glass entryway facing west. Think about that for a minute. But they want it because based on the building site and where the building's going to be oriented and what the owner wants, that's the important thing, the owner wants big glass entryway. It's going to violate what 90.1 says, or in this case, this standard. Well, you can do trade-offs. If you do other things that are more energy efficient to offset what you're not doing, the net result of the building's okay. And so this performance path basically gives you options to think outside the box and give the owner what the owner wants and still be compliant with the code. It's an easy, simple way of saying it. Okay? First area, and I'm just going to go kind of give you some examples here, shotgun, okay? Chapter 5 is on sustainable sites. Here they're basically trying to do a couple things. One, they're trying to minimize the impacts of hard surfaces and elements around your building or on your building so that you're creating this urban heat zone, if you will. Okay? The other thing they want to do is limit the amount of energy that's actually going into the building. So you'll see that they want shading on the exterior walls going up. Vegetation, false wall, sun screens, whatever combination, you got to have shading. And then there's some minimum requirements on the roofing. Again, trying to minimize those impacts to the site. For those of you that love acronyms, my industry is in love with acronyms, HVAC. So here's a new one, BUG, backlight, uplight, glare. There's new standards now on outside lighting of the building so that we can minimize that and minimize this night illumination effect so that you're in a space shuttle, you can see the glow of the East Coast as you're flying over, okay? Much more stringent requirements than code 90.1. Water use. They do not want you to have this type of irrigation system. They want you to have smart irrigation with zoning and smart irrigation control so that you're not wasting water. How many of you seen sprinklers go off in a rainstorm? Yeah. And a bad one like this that's going to do more water to the sidewalk than the grass. There's code standards in there related to the EPA and the DOE on standards for water use appliances. And the big thing here is metering. Any building that consumes more than 1,000 gallons of water per day, building must be metered. And then there's many elements, sub-metering, that also has to occur. Some of those are HVAC related because we are using water in our heat rejection systems in many buildings. So if we've got cooling towers, we have to have water metering. If you have also, anybody familiar with what's called drift on a cooling tower? Okay, drift has to do with the water and the air that's coming out of a cooling tower. Okay, the way a cooling tower, first of all, I should not make this mistake. You all know what a cooling tower is? Okay, it's an object outside that's cooling water by using the wet bulb of the air. And the wet bulb temperature of the air coming in as the fans draw air in, the wet bulb temperature is a lot cooler than the dry bulb temperature for the most part. And so I'm taking that element of the air and the water to promote some evaporation of the water that's in the tower so I can cool the rest of the tower. Think of this, when you step out of the shower, you haven't dressed yet, you haven't even toweled yet, you're just dripping wet. Do you get a chill on your body right away? Typically. Yes, and that's because the water on your skin is trying to evaporate. And when that happens, it's pulling energy from your body because your body temperature's in the 90s. The room's not that warm. So you're the heat sink that's creating evaporation on your skin. That's a natural phenomenon. That's evaporation cooling. That's what a cooling tower is. Okay, well, we have to limit how much of that evaporation is in the air and potentially drifting out of the tower onto something else, because that's an environmental issue. Does that make sense? Okay. Condensate collection. When we go through a mechanical cooling process and we have a cooling coil isn't just doing sensible cooling that you can feel, it's dehumidifying the air, taking moisture out of the air. And what happens in most mechanical cooling devices, most air conditioning systems, is that condensate goes through a condensate trap down the drain to your wastewater disposal. Well, here we're now entering the age of we're going to recycle that water. So we have to build into the building a collection system, and this is now saying any unit that's over 65,000 BTU, so basically any unit that's over about 5.5 tons in cooling, has to now have a collection system for its condensate. That's a pretty small unit. That means a lot of your shopping centers, small banks, small office buildings, which might employ units this size or bigger, now if they want to follow this code, they have to have gray water collection. That's a big deal. I don't know why they call them green roofs, because they're never green. Well, that's probably because it was early in its life. Every one I've ever seen has been just brown. But you can't use potable water, which is pretty much self-explanatory. Here are some subcategory areas where you have to measure water. You have to have metering. And some of it is in areas you probably wouldn't even think about. If you've got steam boilers in your building, you have to have metering to the make-up water system that makes steam if your boilers are over a certain size. If you have reclaimed water, I mean, fit any of these categories, you have to have now measurable metering on all those water supplies. Chapter 7, energy. And I'm going to try to go through as quick as I can. These are the goals that we're trying to meet. 30% better than whatever the previous energy standard was. Okay, which is a big deal. Because the previous, and then why is we're going back to the previous energy standard is because that's what most states are using for code. Like right now, Michigan uses the 2010 version of 90.1. So essentially what they've done here is they've said, okay, the intent here is we want to be 30% better than the energy standard that you're probably using for code right now in your state. Okay? There's an appendix in the back that gives you guidelines for creating what's called benchline marking of energy consumption of a project you may be working on. In 90.1, that was Appendix G. There's a similar appendix in this standard that does the same thing. They also, there's an area that they're trying to reduce what's called peak load. That once occurring in the year that you have to design for, that only happens maybe 1% of your operating hours of the building annually. They want you to do some things to reduce that. And then the guidelines in almost every area are more stringent than 90.1, which is the current code. The other thing that they're doing here is they're trying to follow some existing things that are already out there. Architectural students, you should be familiar with the AIA 2030 challenge, I'm assuming. Okay. How many of you are familiar with the term ZEB? Okay. It's another form of saying the same thing. So the intent here of this energy chapter is following a lot of the things that are already out there in our industry. Under the mandatory, you have to provide the means. You don't have to provide the panels, but you have to provide the on-site means of PV panels for energy generation. You don't have to provide the panels yet, just have the space allocated for future installation if you choose to do so. Okay? Exceptions are, there's a couple of areas of the country. We are not in that accepted area, so don't think we're excluded from that. And there is one other way we can get out of this. If the owner's intent is, I'll just buy green power, then you don't have to do it. But then they have to buy green power forever. And the reason that's there, think about this. If you're in the very heart of Grand Rapids and you wanted to build a brand new 10-story building, do you think you could actually put enough PV on the roof of that building to go net zero? No, you can't. So to be compliant, you'd say, okay, I'll buy green power. Mandatory requirements for all metering. This kind of goes back to the water metering, but this is just all meters in general because most meters are electrically driven. All meters must have the ability to tie into an automation system in the building for a remote readout, and they must be capable of data storage, up to 36 months of data. Now that's either the meter itself and or tied into the automation system where you're doing logging and trending. Okay, it just says you must have data. There are a lot of subcategories of things that must have electrical metering of power or energy. It's a long laundry list. Many of these are easy to hit the threshold limits on. So those are the mandatory things. And I didn't really cover them all. I just covered what I thought were some important things. Now we can either go prescriptive path or performance path, and I'm going to give you a couple of examples of both. On the prescriptive path, okay, you said you were going to have areas on the building for PV. Now go put it there. Okay, follow the guidelines and put those panels there, and or be willing to buy it at this rate. Okay, they give you some guidelines of what they want you to do. If you've ever seen 90.1 for, okay, what U value do I need for the walls? What's my solar heat gain factor for the windows? What's my whatever factor, lighting density, watts per square foot that I need for indoor lighting, whatever it might be. There are a new set of tables now for all that stuff in this standard, 189.1. And they're more stringent. I'm not going to get into the details, just trust me, they're much more stringent. So in every case, the wall components, the roof, the glass, everything that's in the building, you cannot use what someone touted as, yes, meets code. Won't be good enough. Got to go better. You got to do overhangs, and that's to minimize the solar load. They also want you to look at orientation, east-west versus north-south. They want the north-south to be bigger than east-west because they don't want the morning load and the afternoon load to overpower the building. Okay? And this is pertaining to climate zones 1 through 5, which we're in right here. All of Michigan is in. Demand control ventilation. People know what demand control ventilation is in a building? It's basically throttling and controlling the amount of fresh air I'm going to bring into the space, because what they originally set up for how much air you need, like for this room, for example, all the diffusers, I'm bringing in air so you feel comfortable. Well, part of that process is how much fresh air from the outside am I bringing in? Well, the code says, look at all the seats. That represents a body. I'm up here, that's a body. There's people walking around, those are bodies. They all have to be part of the original design intent for how much fresh air you need. Are we going to be here from the start when the doors open to when we leave? Everybody? No. Not reality. So demand control ventilation basically says, okay, if you have a metric to be able to throttle that and measure against it and be able to control it, and the easiest way to do that is CO2 detection, because that's what we exhale. So if I can limit that, then I don't have to treat that outside air and I can save energy. And there's guidelines here on how to do that. Economizer kind of follows the same thing. We live in a northern climate that says, hey, instead of taking mechanical cooling right now at this time of the year, I'm going to bring in fresh air outside. Some people call it free cooling. It's economizer cooling, okay? And there's ways to do that. Nothing before this standard came along forced you where an owner had to do that. Now there's guidelines that say, okay, for these climate zones, here's where you have to do it. So basically, in our climate zone, it says any unit that's over 33,000 BTUs, which is not very big, it's like a residential unit, you have to do this. Okay? And you also have to do some other things. If you have, everybody know what VAV is, variable air volume? Okay. Variable air volume is a way of sending out a steady temperature of air, and the brain dead in our industry is 55-degree air just because it works. not because it psychometrically solves anything. It's just that everybody's picked that because most of the time it works. If the air comes out at that temperature, then to regulate the temperature in the space, I'll just vary how much air I bleed into the space based on a thermostat. And so the damper regulates how much air I need. Okay? But nothing ever back at the unit changes the temperature of the air. So I got to spend all that energy back at the unit. This says, hey, at certain times of the year, you don't need that cold of air. In the dead of winter, remember part of the reason I'm driving that temperature down at the unit is to take moisture out of the air and dehumidify the air. In January and February, we've got buildings that have low humidity. So why are we taking all the moisture out of the air? Let's set the temperature up a little bit. Okay? So this has to do with what's called supply air reset. There's also other things that deal with in what's called reheat and fan. These are the two big areas that suck a lot of energy in our systems, HVAC. If out of this box, if that air is always cold, and to satisfy the ventilation requirements, I have to keep pumping air in here, I may have to reheat that air, make it a little warmer. And you can do that a couple of different ways, but there's limits now on what you can and cannot do. And there's also limits on how much the fan back at the unit can consume on its fan energy to deliver the air to all the spaces. Which means the designers now have to think a little bit differently. And one of the ways to do that is to make the equipment a little bigger, make the ductwork a little bigger, so it doesn't take as much energy to move that air. Think about this. If you had two straws, instead of blowing, say sucking, you're drinking with them. If you had a really skinny straw versus a fat straw you don't have to suck very hard. The skinny straw, you're going to suck your brains out to get something to drink. Okay? That's to do with pressure loss. Energy recovery. There's new guidelines in there now about what air handlers in buildings have to do. Mandatory energy recovery at the air handler. Much more stringent. I could have an air handler with a really low percentage of outside air, but it's a big air handler in our climate zone. Now has to have heat recovery. And it's a type of heat recovery that has a certain efficiency, minimum 60% efficient, which now means I'm into enthalpy heat recovery. Anybody know what the word enthalpy means? It means total energy, sensible and latent. So now you're into what's called heat recovery wheels. A lot more space, a lot more energy, a lot more money up front, first cost. Peak factor. It's basically saying I want to shift the peak of when because the worst case scenario, this building consumes its most energy, point in time, or any building like this. When do you think that usually occurs in any building in North America? No. Okay, I'll make this simple. Think about the things that create the need for consuming energy. The air conditioning's got to be on 100%. It's not winter. Okay? Lights have got to be on. People got to be there. And so everything's got to be on. It's usually at 3, 4 o'clock in the afternoon in the middle of the summer, worst day in the summer. Okay? However, if that's common here, it's common in every other building. That's what the utility company has to prepare for when they size their power plant, the distribution of all their power lines, their transformers, and their grid system. They have to design for that worst case scenario that might happen maybe for a 2-hour window every year. Okay, and that's why in the East Coast and many very heavily densely areas they have what they call demand charge. The demand you're going to see, you have to prepare for it as a utility. What they're trying to do here is lessen that demand peak. Get creative on what you do in the building so you reduce that peak that only happens once in a while. like once a year. For those of you involved with lighting systems in buildings, man-made lighting systems, there's some new factors that say you have to reduce your wattage in these spaces. It's a power factor. Okay? So you got to get better lights, essentially. Areas that are what I would call connecting areas or common areas, they want you to reduce the lighting levels in those area buildings. Yes? Oh, I thought you were asking a question. Natural daylighting. If you've got natural daylighting combination with man-made lighting in areas of buildings, they want you to have auto dim controls so you can take advantage of that natural lighting. Okay, performance based on energy. I'll try to go as quick as I can here. Basically, the big thing here is if you do your energy modeling and do everything correctly and prove that you're doing it, that's fine. Follow all the guidelines on prove it. The one step they want you to move towards that you're not doing now. There's guidelines in there. They want you to create a carbon footprint for the building. Take all that energy that you've created in your studies, apply these factors and come up with a carbon footprint for the building. And this should be the number one thing that tells you where we're going as an industry down the road. 5? 5. I'm going to go real quick. We are moving towards this as an industry, carbon footprinting for buildings. Government standards down the road, and people I know in the industry are telling me this. Project out 10 years, all these tables and all the compliance that we see in all our energy standards won't exist. One thing will. What's your carbon footprint of the building? Period. Do whatever you need to do to make it happen. That's where our codes are going. Indoor environmental quality, they basically don't want that. There's rules and regulations in there on ventilation. This is the biggest takeaway you should do. You cannot overventilate and get LEED credit. Doesn't exist here. Don't want it. Don't do it. They want you to get smart on how you ventilate your buildings because ventilating your buildings costs energy, which is why Matt had natural ventilation in his. Okay? Excuse me. They have also some guidelines here for if you have large areas with roofs right above. They want you to do natural skylighting in those areas. They also want you to use side linings. And look at this picture, it's real important. See the partition there on the sidewall? They want a certain area of the windows to now have the ability so that you have different shading requirements. The top, no shading. Bottom, shading. Where there's no shading, that's where you're going to have all your natural daylighting occurring, so it reflects up into the ceiling. You want that sun there. Projections on the outside for shading, there's some guidelines there on what they want you to do, and here's a big one that's new. There's standards on VOC elements within buildings, volatile organic compounds. And there's a table in another chapter that deals with that. There's also standards that are pretty similar to LEED when it comes to waste management through the construction process. Obviously, some of these things are just like LEEDs. They want you to, no refrigerants on the site. They want you to have plans for storage and recycling. This is different than LEED. Very stringent rules on commissioning. Commissioning process also starts on buildings that are small as 5,000 square foot, full commissioning. That's just not airflow. That's everything. Because look at all the things that should include HVAC, building envelope, lighting, irrigation, plumbing, domestic water, renewable energy. All those things have to be a part of the commissioning process. And the commissioning agent needs to be involved during the design review process. Not just a commissioning agent when, hey, Mr. Owner, take the building. Commissioning agent has to be involved early. You should have an erosion control, better than this one. Indoor air quality, basically they want you to have certain guidelines to make sure your indoor environmental quality starts from day one being good, which means you don't use your permanent air handling systems during construction. Okay? Don't let the coils that are going to transfer energy be the filter and comb for all the construction dust. And you should also have a determined flush out before you start your indoor air quality or indoor environmental testing. You know what a flush out is? Flush out is basically when I'm going to move a lot of air in the building, turn up the heat in the building, and bake the building and get rid of a lot of the VOC buildup in the building. Off those chairs, off the carpeting, off the walls, off of everything, and get rid of it. Here's something that's brand new. VOC measurements of what can be acceptable limitations in buildings. The first place I've ever seen it. This is code, which means thou shall. You also spent a lot of money in the first part of the standard talking about site development. Well, let's have some sustainable practices at the end to make sure that you keep it. That includes M&V processes on water, for tracking water efficiency and use, and energy. You got to have it in your building energy management system to be able to track it hourly, monthly, and show all the trends and the output on what you're doing with energy. And here's the biggest thing that I can hang my hat on and say why this standard's so much different. And it really embeds what Matt was talking about in the big picture of his presentation. We get stuck in this country way too much with one simple thing: bid day. Everybody is hung up on the cost. And when they say life cycle study, how long do you think they go normally? 25 years. If you're lucky to have a life cycle cost study, Jim, was it 10 to 20? 10 to 20 years. Which then the natural response is, okay, in year 21, you're going to knock the building down? Okay. This right here is average commercial building in North America, or should be. 50 year. Our students, when we challenge them in class to do a life cycle study, we go 50 years. Because that's real. And the big difference where I applaud ASHRAE and USGBC and Lumina Engineering Society when they put this in here, because it is sending a message. What do you think Europe uses for life cycle, or their ideal life cycle? It's both right. Centuries. Here we're talking decades. So that's the big takeaway. And this is the first step towards it. So this standard is actually trying to put some meat to that code compliance of what is life. Now, I got 2 slides and I'm done. Suggestions. If you're going to follow this standard in the real world, you have to have a team-based approach, which Matt was kind of endorsing up front. You have to have early buy-in, and because every decision you make up front has huge implications. And when you're looking at all these elements, those are early decisions. They will have big-time ripple effects. And here's the biggest thing. In fact, this is the one thing that I'm trying to stress to my industry right now. When normal construction process right now, when you turn a building over to a building owner, what do you turn over to them? Drawings, specs for how the building was built, commissioning report, submittal drawings for all the elements that are in the building, and then maintenance manuals. Does anybody turn over a report to the building owner that says, you know what, when we sat down and we looked at the concept idea of this building, this space, what was the intended utilization of this space for the occupants in this space and all the elements that impacted the occupants in this space to be able to give you your net design of what was delivered. Is that in spirit ever documented to the owner, such that if down the road the owner changes his mind and changed the utilization of the space? Is that ever documented? By the way, if you want to be sharp with your firms right now, here's an area of opportunity. You could change your firm. Another service. Building operating plan, BOP. What's your building operating plan? What's the intent of this space? What's the intent of that space? Because if your intent changes, it changes the dynamics of everything we're talking about, which then touches the elements that create energy, the environment, etc. And I'm going to finish with this last slide, and I love this slide. It's so simple, but it's yet so powerful. The three things from a financial standpoint that affect the life cycle of a building are three basic areas. First, cost. How much does it cost to construct it? Maintenance. How much does it take in money and supplies to maintain the building? That's repairs, day-to-day maintenance, annual maintenance, etc. And then operation, utilities, and anything else that's tied to the operation of the building. We, as an industry, because of the generation of bid day, are so wrapped up in this that we tend to not look at the next two. And over the life of the building, it's the smallest piece financially. With that, thank you.